Welcome to the Friday Forum for May 9th, 2025. This is the 229th Friday Forum in a series hosted by ICLR, the Institute for Catastrophic Loss Reduction. We are Canada's leading source for disaster resilience knowledge. Each month, we present recently completed research related to ICLR's mission to make Canada more resilient to natural disasters. I'm your host, Dr. Keith Porter. I'm ICLR's Chief Engineer, and I'm speaking to you today from Toronto, Ontario, the traditional territory of the Mississaugas of the Credit, the Anishinaabeg, the Chippewa, the Haudenosaunee, and the Wendat people. It's now home to many diverse First Nations, Inuit, and Métis people. If you joined us last month, you heard Shiree Kotar, Brent Doberstein, and Charmaline Mendes Millard talk about managed retreat and home buyouts. And next month, on June 13th, our friend Connell Miller from the Canadian Severe Storms Laboratory is going to tell us about the Northern Mesonet project. Connell's team is aggregating weather sensor data from multiple networks across Canada in a single user interface. If you or a colleague use weather data, tune in. It's going to be really interesting. And remember that you can find recordings and the speaker decks for all of our Friday Fora at www.iclr.org/workshops. Now today, Professor Mathieu Bourbonnais of the University of British Columbia at Okanagan is going to tell us about real-time monitoring and prediction of wildfire risk for response and mitigation. He and his colleagues have created a system that uses low-cost Internet of Things devices and artificial intelligence to monitor fires and predict fire risk for the next 3 to 5 days. The system is up and operational in British Columbia, and it's helping wildfire agencies and municipalities to better prepare for and respond to wildfires. I'm looking forward to hearing about how this system is actually making a difference in fire outcomes. A little bit more about our speaker. Mathieu performs research at the University of British Columbia, Okanagan, in fire risk and wildfire management. In addition to the near real-time prediction and monitoring of wildfires that he's speaking about today, his research team seeks to understand how ecosystems respond to changing fire regimes. He co-directs the UBCO Center for Wildfire Coexistence, and he leads the Earth Observation and Spatial Ecology Lab. In a prior life, he was a wildland firefighter, and he has an exciting announcement to make about prescribed fire today. I had the pleasure of visiting UBCO, where he and his colleagues taught an intense short course on computerized wildfire modeling, and that was really fun. Now, before we begin, here's our agenda. Our webinar is going to last 90 minutes. Our speaker is going to present for about half that time. Then I'm going to moderate questions for the rest of the time. Please feel free to chat your questions into the Q&A box. I'll try to pose your questions in the order they appear in the Q&A box. If we have a lot of questions, I may only pose your first question, then I'll move on to others, then I'll circle back to your additional questions. Now, our webinar is recorded, and ICLR is going to post the slides and a link to the video by Monday. So if you have colleagues who couldn't attend, let them know. You'll find the video and a PDF of our speaker's deck at www.iclr.org/workshops. With that, I'm going to turn it over to Mathieu. Take it away.
Hello, thanks very much for the introduction, Keith. Hi, everyone. my name is Mathieu Bourbonnais. So I live and work on the unceded ancestral territory of the Silk Okanagan people, so in Kelowna. Today, I'm actually joining you from Toronto, though, just here for some meetings, and I'm happy and excited to be talking about some of the work that we've been doing in wildfire risk monitoring. So a little bit of what I'm going to talk about today, just to kind of set the stage for why we've been working on this kind of system for the last few years. I'll talk a little bit about wildfire in Canada, sort of the state of what's been going on over the last few years. I'll talk a little bit about how we conceptualize wildfire risk, mainly from a operational kind of standpoint. This might be a little bit different from like a liability sort of perspective. Then I'll talk about some of the current models that we use and the main one, which is the Canadian Forest Fire Danger Rating System, before moving into some of the technologies and models we've been developing and how we're integrating these systems in with different agencies and communities and looking at risk mitigation. So a little bit about myself, though, just to contextualize, because I'll have a little bit of this throughout the presentation when I'm talking about things. So before I went back to school and got into research, I worked as a wildland firefighter for the better part of 10 years. So I worked with the Alberta Wildfire Repel program out of Alberta and with Parks Canada in their fire management program. And it was actually in 2011. So this is actually a little snapshot of my rappel crew that year. So we're actually rappelling in the morning onto about a 900,000 hectare fire, and I'll have the satellite image in the next video. But I think it's this kind of work and having this sort of like operational background that's informed a lot of my work. Because when you're working on a crew like this and you're thinking about models and doing all this kind of work that we do now, when you're working in this kind of environment and working on these big fires, it's incredibly busy, can get fairly chaotic. And so in our work, we're oftentimes thinking about if it's going to be a crew that's going to be using this kind of information, or it's going to be a wildfire manager or an operations officer or something like that. How do we tailor our information products to give them the amount of information they need to make decisions about wildfire management or operations or risk mitigation without overloading them with all kinds of detail? So you can kind of see the fire in the back there. Our crew, I think this morning, we were flying out to rappel in to cut in a helipad so that we could start getting other crews in that morning. So this fire, like I said, in 2011, this is what actually led me to go back to school. This was the Richardson complex. So this was following the Slave Lake fire earlier in May. And the Richardson complex burned from Fort Mackay, so just north of Fort McMurray, all the way up to Lake Athabasca. So at the time, it was the second largest fire in Alberta's history, so about 900,000 hectares. And it was so large that in our morning briefings, rather than getting just like little maps, we were actually getting satellite imagery showing like what was the estimated perimeter, which got me interested in kind of geomatics and led me to going back to school and kind of getting into this kind of research. So I'll come back to some of the satellite imagery and how we kind of use this in our models a little bit later in the talk. So a little bit of wildfire in Canada, and I won't kind of belabor the point here because I think we've seen a lot of this in the media over the last few years with our wildfire seasons in Canada becoming more destructive and having bigger impacts. And so this is just a map from the 2023 wildfire season in Canada. And so obviously that year we burned around 15 million hectares. It depends on who's doing the mapping. And we followed that up in 2024 with another big wildfire season. So we had around 5 million hectares burned across Canada. We didn't see the same range of scope in terms of the regions that were impacted as severely. So in 2023, if you just kind of look at the map here, we had about 4.3 million hectares burned in Quebec, 3.6 million hectares burned in the Northwest Territories, 1.2 million hectares in Saskatchewan, 2.7 million hectares in Alberta, and 2.3 million hectares in BC. For most of these regions, these broke all previous records for that region in terms of area burned. And when we talk about millions of hectares, it's worth noting also, Newfoundland burned 19,000 hectares, and between Nova Scotia and New Brunswick, there was 24,000 hectares burned. So we saw these impacts across a lot of areas that haven't had sort of the same wildfire activity compared to areas like BC that have had kind of recurring record-breaking seasons. What was interesting, though, is going into 2024, when we look back at it, a lot of folks have kind of expressed, oh, it didn't seem that busy, but 5 million hectares burned is actually the second highest total we've had since 1989. It just kind of paled in comparison to 2023. And so a lot of the work that I do, and a lot of the work that we do currently is in British Columbia. And if we just kind of zoom in on it a little bit, because it's been kind of on the leading edge of kind of where a lot of the change has been happening. This is a map just reflecting up to the 2023 season. You could add 2024 into this, but 5 of the worst fire seasons on record have happened in the last 8 years in British Columbia, in terms of sort of our recorded history with wildfire perimeter mapping. And you can kind of see the distribution of the fires in this map. And it really, we've seen impacts across all the ecosystems that we have in BC, maybe a little bit less in some of the coastal regions, but we're still seeing a lot of change in those areas. So 2023 was a really big year, kind of broke the record from 2018, which was 1.8 million hectares. So we almost added another million hectares in area burned. And if you look at the bottom graph there, those are just the proportion of area burned by some of the biggest fires per year. And we're still seeing the same trend that we've always seen in Canada, where a lot of our area burned is a reflection of a few fires that are extremely large. And so in 2023 in British Columbia, the Donnie Creek wildfire burned about 600 to 700,000 hectares, which was the largest in BC's history. So why is this happening? And just to kind of go through this really briefly and not dig into too much of this into too much detail, but why are we seeing these changes in wildfire seasons? Why are we seeing our risk change so dramatically compared to what we've come to expect? And even when I reflect back on my career as a wildland firefighter, things have changed a lot since 2011. What crews deal with now in a wildfire season, you can have crews putting in 100 fire line days in a season. And in the early 2000s, it might take you 2 to 3 years to get 100 fire line days. So the scale of what crews are dealing with now is far different. And so there's a few main factors, and one of them is that our climate and weather is changing quite rapidly. And so when we've looked at this, just for British Columbia, so we did a study where we looked from the early 1900s all the way up to about 2021, in terms of what was happening with our climate in BC using weather station data. And basically, what we found is that you kind of hit the middle part of the century, and we saw this shift kind of happening as you got to the 2000s of increasing temperature, precipitation also increasing. Although what we found is that this increase in precipitation overall for the province has been offset by those higher temperatures. The cumulative moisture deficit has gone up. And basically why that is a reflection of kind of how much moisture our fuels are kind of retaining relative to kind of the temperature that we're seeing. So if you have a higher cumulative moisture deficit, you basically have more drought. The number of frost-free days has gone up. The date that we hit the 2% of the cumulative annual area burned, it's kind of a funny statistic, but basically it's a reflection of historically, how much area burn would we have, and what date do we hit that 2% of that is going way down. So our fire seasons are becoming way more active a lot earlier. Our area burn has gone up a lot. You can see that in the bottom left graph there, just this really big increase, sharp increase in BC starting in the early 2000s. But our number of fires over 20 hectares has actually gone down. And this is a reflection of fire suppression. So, we are still very effective at suppressing a lot of small fires, but those fires that get away, or that actually grow large, are burning a proportionally bigger area than they have kind of historically. If we look at this in relative terms to Canada, and then just focusing in on the 2023 season, you kind of see the same patterns. And so this is kind of a map done by, or a study done by colleagues at the Canadian Forest Service, just looking at what did we have in 2023 in terms of climate and weather that kind of drove a lot of the fire behavior that we're seeing. And we saw really, really high temperature anomalies across a lot of the country, extending into the north, into the Arctic. And compared to historic values, kind of record-breaking sort of temperatures across the country. We saw significant precipitation anomalies in terms of essentially reflecting kind of long-term drought that we had across a lot of the West and into some of the boreal areas of southern Northwest Territories. And then we had a lot of these vapor pressure deficit anomalies across the country pretty persistently for a lot of the summer. And vapor pressure deficit is basically just allowing us to compare, or assess how much moisture the air can actually contain based on kind of the temperature of that air mass. And so if you have a really large vapor pressure deficit, what that essentially means is that your fuels, so all that material and biomass on the ground, is going to readily lose that moisture content into the atmosphere if you have a large pressure deficit. And what we saw also, kind of going to the graph here on the right, is I'll talk a little bit about more what we mean by fire weather days, but we're seeing more extreme fire weather, reflecting kind of this temperature and precipitation kind of trends that we're seeing across the country. And so if you look at the little graph down here, this little red line is kind of the mean sort of fire weather we might see historically across Canada, across kind of the fire season, which extends from April to September, but really is getting longer. So our fire seasons are increasing by about 30 days over the last kind of decade. And this graph here, these spikes are actually the extreme fire weather observations that we had nationally across the country. And so we had a lot of really high spikes where fires were just or was a high likelihood of having a fire. And if we did have a fire, growth, you're expected to see a lot of very aggressive growth. So our climate and weather are changing quite rapidly. The other thing that's happened, and this is going to vary across the country in terms of the ecosystem and what's going on. But if we focus a little bit on the West, our landscapes and our fuels, and fuels again is kind of biomass that's available to burn, they've changed dramatically. Both a reflection of kind of how we've managed landscapes for natural resources and forestry, and how we've replanted, post-harvest, but also fire suppression by taking fire out of the landscape. In a lot of areas, we've essentially allowed it to kind of homogenize in terms of not as much heterogeneity in terms of fuel types that are on the landscape that would inhibit large fires from kind of growing. So this is actually just a repeat photography by the Mountain Legacy Project from a site actually near the Okanagan. On the left, the images from the early 1900s. And this is kind of the same image taken kind of in 2018, sort of. And we see this pattern across a lot of areas in BC, in Western Canada, where you just have far, far more conifer trees than we would have had compared to some of that historic reference imagery. And that really plays out in what we see on the ground. So on the left, where you kind of see some of that low intensity fire going through this ponderosa pine stand and Doug fir stand. Historically, like if we think about interior dry forests in BC, we would have seen a lot of stands like this where fire return intervals would have been quite high, reflecting both indigenous cultural fire and also lightning fire that would have put fire back into a landscape fairly frequently, depending on the ecosystem. So in a system like this, you might have seen a fire come through anywhere from, based on our modeling, from 5 years to 40 years, and in higher kind of elevation ecosystems, it could push to 60 to 100 plus years. But there was a lot of fire on the landscape, and in dry interior forests, it kind of created this sort of open savanna-like kind of ecosystem where you had a lot more open meadows and grasses, and actually deciduous sort of species intermixed with all this kind of conifer. What's happened though is, as a result of kind of just how we've managed landscapes, in the middle we talk about sometimes that we've redistributed fuels. So by harvesting, if we leave residual slash or these kind of things, we're just moving that fuel complex around, and we're creating sometimes new and novel fuel complexes that fires can burn in. And then in C, there over on the very right, that's kind of just an example of kind of heavy ingress of new conifers and new regen coming into an area that creates this really, really dense multi-story layer that, if a fire gets into in the right conditions, can lead to really, really aggressive fire growth. And that's oftentimes a reflection of fuels have changed a lot. And reflecting that, what we're seeing is just that our fire regimes, and so a real basic definition of a fire regime would be just kind of the spatial and temporal patterns that we'd see of fires across the landscape. So both like how often we see fires, how big are they, What type of fire behavior we oftentimes see? Is it like high intensity crown replacing fire? Is it low intensity surface fire? That's changed a lot across a lot of our ecosystems in Canada. And so this map is just a snapshot of the Okanagan going up to 2021. And you can see if you just kind of look at the polygons or the colored kind of blobs there on the screen, that the size of the fire is actually has changed a fair bit just at first glance. So in the early 1900s, we'd gotten out of cultural fire by that point. It was pretty much made illegal in the early 1900s, but there's still a lot of kind of settler burning and sort of fire related to kind of natural resource management. And then into the mid 1900s, as we got into fire suppression, fires really, really decreased in size. We were suppressing them quite effectively with kind of the industrialization of fire suppression using helicopters and planes. And then in the Okanagan, kind of going back to that earlier slide I showed, you see this really rapid increase in fire size happening in the early 2000s. And obviously in 2003, we had the Okanagan Mountain Lake fire, Okanagan Mountain Park fire down here that impacted the community of Kelowna. And then here in 2021 would have been the White Rock Lake fire that impacted kind of the west side and got into Okanagan Indian Band territory. So we're seeing a lot of change. And if I could generalize a little bit, and this doesn't kind of hold everywhere, but we can sometimes think about fuels and fire regimes and kind of there's a few different classes, but oftentimes we think about them as either fuel limited or climate limited. In a fuel limited system, something like an interior dry forest, there's just not enough fuel historically to kind of sustain really large fires. So you'd have so much fire in that system that the fuels can accumulate to a certain degree to allow large destructive wildfires to occur. Well, we shifted away from that in a lot of our fuel limited systems. Similarly, in climate limited systems, so areas that are going to be wetter, like our coastal systems, or kind of cold and dry, and might not have kind of the same period of really dry conditions over a long time, like the boreal. They're going to be more climate limited. There's a lot of fuel that's available there to burn, but because the climate is a moderating factor, you just don't get the opportunity to get those big fires in these systems. That isn't quite happening in the coast yet, but we're seeing a lot of shift in this kind of climate limited system in our boreal systems that are burning historically at high intensities, but are just experiencing really, really high area burned over the last few years. So a lot of stuff has changed, but now how do we go about, or how have we approached assessing risk with all this kind of change happening? And there's quite a few ways that we approach this. And pardon me. I quite like how sort of this paper by colleagues at Natural Resources Canada and the Canadian Forest Service sort of set this out, is that when we think about risk, there's a few different things that we need to think about. And I'll go into primarily for the rest of the talk a lot about what goes on with kind of the likelihood of fires and the occurrence of fires and how we assess fire behavior with that. But when we're assessing risk associated with wildfire, first we need to sort of understand, like, what is the likelihood of that a fire is going to occur? And there's certain models that we use in Canada to assess, what the fire danger is for a day or historically over time for like a given region. We also want to understand sort of like what the expected fire behavior might be for a day given certain conditions. And that matters a lot because the fuels are going to drive that, the weather is going to drive that, but it also influences the type of impacts we might see as a result of a fire if it does occur. So being able to predict that and understand how it varies spatially and temporally is pretty important. And what that leads into is an understanding essentially of our exposure. And when we're thinking about risk. And so exposure is, exposure to wildfire to different values that are on the landscape. And we oftentimes think about this in the wildland urban interface. So from the same paper, there's a lot of focus on this right now with fire smart programs and others. The house on the left there probably has low exposure, even given certain fire behavior, because it doesn't have combustible fuels around that house. Whereas the one on the right has high exposure because it's just integrated right into that WUI, and it has a lot of fuels available to burn around it. So while we think a lot about like the built environment, and especially homes, when we're thinking about exposure and values, there are a lot of other values that are out there on the landscape that our partners and the folks that we work with are interested in understanding. So, timber is a value. So what is the risk to timber values across, a province like British Columbia as a result of changing fire regimes? What are the impacts or potential exposure to our community watersheds in different parts of the country, and also the infrastructure that's out there, our power grid and other kinds of industrial infrastructure? And also, what's the exposure to wildlife habitat and some of these different species that rely on very specific conditions to kind of fulfill sort of their life history needs. So we focus a lot on exposure in terms of the built environment, but it's a lot broader than that when we think about values. And so when you start pulling those things together and you think about fire behavior, exposure, and values, you start then being able to conceptualize or understand a little bit what the potential impacts might be. And so for that house that, is surrounded by a lot of fuel, given certain fire behavior, it's going to have high exposure. We'd expect to have then high impacts where, maybe we're going to lose that house or we're going to lose a lot of homes in that community. And so combined, that likelihood and impacts gives us essentially an estimate of risk. So it's not just that a fire is going to occur, but like what might that fire do and what might the impacts of that fire do to give us an idea of risk overall. And we're a big country. We have a lot of forest, and it's not just forest that burns, grasslands burn. We have a lot of different fuel types across the country, hardwoods, that are going to burn in different ways. And reflecting the size of the country, we have a lot of infrastructure that is embedded in landscapes that are fire prone. And so it's a little bit, 7 years ago, but colleagues at the Canadian Forest Service did some mapping where they assessed, nationally we have about 33 million hectares of wildland urban interface. It's probably higher than that. I think in a lot of communities that we work with, you just see expansion into the wildland urban interface. It's where we can build. And with, some of the stuff with housing that's going on, how are we going to continue that expansion into that urban interface? In terms of the wildland urban interface industrial, so this is anything to do with large kind of industrial mines or oil and gas infrastructure, those kind of things. We have about 11 million hectares of that. And in terms of infrastructure, our power grids, our roads, other kinds of infrastructure, we have about 110 million hectares. So when we think about risk mitigation and how we're kind of approaching this and the scale of the challenge that we're dealing with, there's a lot of risk out there. So understanding how that risk varies spatially, like, around a community, are there certain parts where there's less risk versus more risk? It's really important to understand when we're thinking about targeting risk mitigation to help support communities and agencies. So like I said, when we're thinking about fire danger, like that sort of fire occurrence and fire behavior element of that sort of risk equation or sort of framework that I presented, there's one main system that we use in Canada, and that's the Canadian Forest Fire Danger Rating System. I'm not going to go into too much detail about it, but it's developed by the Canadian Forest Service. Development really started, back in the 40s and 50s, with a lot of acceleration of that development in the 80s and 90s. So this is a relatively old system that we've relied on. We use it operationally. It does have a lot of value operationally, and there's a lot of things it does well. But I think with what we're seeing in terms of changing fire conditions, there are challenges associated with this system. And I'll kind of talk about those a little bit. So there's two main subsystems of the CFF-DRS. One of them is the Fire Weather Index that I'll describe in the next slide, and the other is the Fire Behavior Prediction System. So most people in Canada actually interact with the Fire Weather Index every day, and I'll kind of show an example of that. But basically, what these two systems do is they take weather, fuel conditions, topography, sort of the things that drive fire behavior and fire occurrence, and then we translate those into fire danger and potential fire behavior using models. And so what it does is it gives us an idea of the current conditions, what our next sort of day might look like in terms of fire danger, and also fire danger over time if we're continuously monitoring an area. And we use this every single day in wildfire operations. So, right now we're into fire season. They're using the FWI every single day, and that's an important consideration, and I'll get into that a little bit. And then we also use it for risk management and planning. So a really brief overview of the fire weather index, and I'm just explaining this because it's been an important part of what we've integrated into our system using our IoT sensors. And so basically what the fire weather index relies on as input is fire weather observations. And so specifically, it's going to look at temperature, precipitation, wind speed, and relative humidity. And what it does then is we use, a model to translate those raw fire weather observations into fuel moisture codes. And from those fuel moisture codes, we get fire behavior indices that allow us to sort of assess or predict what we might expect for fire behavior in a given day. So I'll just kind of show you what those different indices sort of look like. So the first one is what we call our fine fuel moisture code. And so it relies on everything: temperature, RH, precipitation, and wind speed. And the fine fuel moisture code is meant to reflect how much moisture might be contained in your really fine fuels. So think about like pine litter, small twigs, anything that's dead and on the forest floor is going to be in your fine fuel moisture code. And so it responds really quickly to changes because they're really small fuels. They respond really quickly to changes in temperature, precipitation, wind speed. Wind can dry out fine fuels, and your relative humidity. And so if we go up in size a little bit in terms of like the size of the fuel, we have the DEF moisture code, which only responds to or only needs inputs of temperature, relative humidity, and precipitation. And so the DEF moisture code sort of is meant to represent that top layer of organic material in a forest floor and a little bit larger diameter dead fuels. So think like, larger branches and things like that. And because these fuels are a little bit larger, they take longer to dry out, and they also take longer to recover if they're drier. So compared to the fine fuel moisture code, which can change rapidly from day to day, the DEF moisture code sometimes can need a week or two to actually kind of recover or lose values, reflecting how much moisture is available in that fuel. And the final one is the drought code. And so this just purely relies on temperature and precipitation. And these are your really, really deep organic layers on the forest floor or large dead and down logs. So think big fuels. And so the drought code that's sort of that long-term drought. So are those larger diameter fuels available to burn based on the moisture content? And just like the other ones, the drought code is the one that takes the longest to lose values, so to dry out, and it also takes the longest period to recover. So if the drought code is really, really high, reflecting, that you have large diameter fuels that are available to burn, it's going to take a lot of precipitation to bring that drought code down to decrease your risk. So that's kind of the overview of the fuel moisture codes. And then basically what we do is we take, or how the model works, is we have these fire behavior indices that we can predict from these fuel moisture codes. So the first one is the initial spread index. And so it relies on wind speed from your stations and then also your fine fuel moisture code to give you an estimate of if there is a fire, how far or kind of how much growth would we expect to see from that fire in the first burn period. So that's kind of like the first 24-ish hours after a fire starts. So if your FFMC is super high, your wind speed super high, we'd expect to see a lot of growth of that fire if we do get a fire at that location. And the second one is what we call the buildup index. And so it takes your larger fuels And it combines them into an index that as that increases, it's basically giving you an idea that your larger diameter fuels are more available to burn. And so what you would expect to see then is more aggressive fire behavior if the buildup index is high. So, if large logs are available to burn, you're going to see some pretty heavy flames coming from that compared to if it's just kind of burning through fine fuels. It'll also put out a lot of smoke, which is another thing that we can kind of look at. So what we do then is we take those together and we combine it into the fire weather index. So the initial spread index and the buildup index gets combined into the FWI. And the FWI is essentially your fire danger estimate. And so every single day during the fire season, every single fire agency across the country, so BC, Alberta, Ontario, Quebec, every single one of them, Saskatchewan, Yukon, Northwest Territories, is generating their fire weather index values using a network of weather stations that they have across the province or territory. And so this is the map of British Columbia. We have about 260 weather stations across 65 million hectares of kind of forest. And every single day they have their fire weather people generating, the maps that you see on the right, which are the raw values. There are temperature, precipitation, wind speed, and relative humidity. Those that then get translated into maps like you'll see every day. So a map like this is the fire weather index. And so anything above 30 is kind of extreme risk associated with fire for that day. It doesn't mean that we're going to have a fire. That relies on an ignition source, which is going to come from people or lightning. But if we do get a fire, what it does is it gives fire management agencies like a conceptual picture of, for this day in 2023, if we have a fire in the southern part of British Columbia, that fire might become a problem just because of the conditions at that location. And so this is really important because we generate these every day. So the fire management agencies need a system that they can work with pretty rapidly. We can't really rely on systems sometimes that take a long time to compute. The FWI is relatively simple to calculate. It's pretty simple to interpret, but there's limitations associated with it because of that simplicity that I'll kind of talk about a bit. The other thing that it does, if you're driving around and you see those signs that say like high fire danger or extreme fire danger, it's coming from this. Like this is the model that's informing the public every single day. The other thing that it does, and to kind of give an idea, is it also provides management agencies with an idea of where they might need to prioritize their resources for any given fire day. So, a day like today in British Columbia, let's say, you'd have lower expected risk in the northwest of the province compared to the south and southeast. So maybe you're not going to put as many resources up in the north to kind of respond to fires because of that. And I'll give an example of that from a few years ago in a few slides. So the second system that we rely on is what's called the Fire Behavior Prediction System. So the FBP, sorry, not the FPV. And I'm not going to get into a lot of this because this is more used operationally. But there's essentially 16 standard fuel types in the FBP system for the entire country. And so what it is we have these 16 fuel types that have been parameterized based on the structure and composition of the fuel type. So up here across the top, you can see a few examples. We have O1, which is grass, C7, which is ponderosa pine, maybe some Doug fir, and M12, which is boreal mixed wood. They have a very specific composition. So we might have the lead species like ponderosa pine. It's going to give you some idea about the structure. So there'll be like a descriptor of the actual fuel type. And then from that, we've parameterized different fire behavior parameters associated with that fuel type, like flame length, fire intensity, and spread rate. So we can take the fire weather index, we can put it into that fuel type using wind speed and other things, and we can predict, let's say, what we might see for flame length in a given day. There's some challenges, though, with the FBP system, and a colleague of mine, Jen Barron, did a study where they kind of looked, when we're mapping this out, we're relying a lot on spatial data. So that could be forest inventories that are done by the provinces, remotely sensed data that's coming from satellite, and we're then trying to map out, like, for a given location, is it O1 grass or is it C7 ponderosa pine? And that matters because we're trying to understand, like, okay, so if the risk is high based on the fire weather index, we get a fire there and it's in C7, let's say, this is the type of fire behavior we might see. The challenge is, though, is that the standard fuel types are really a descriptor. They don't really separate out your different strata of your fuel types from like your crown to your mid-story ladder fuels to your surface fuels. It just kind of gives you this descriptor across the whole thing. And when you're trying to predict for different areas, like, is it an O1 grass fuel type? It really depends on the mapping that's been done. And so when Jen went and did an assessment in southeastern BC, they found that 58% of the places where they went and put in a plot to assess what the fuel type was, it didn't agree with what the FBP system said it was. So this is just kind of example. We have O1 grass here as the example, and below it, we have 3 of the example plots where the prediction is for an O1 grass fuel type, and we have a lot of forest there. And so we see a lot of mismatch, especially in areas like British Columbia. The FBP systems were designed a lot for kind of boreal fuel types. And so this is a bit of a challenge, especially because we rely on the FBP. So this is the provincial strategic threat analysis that's been done for British Columbia. We rely on the FBP to inform kind of what's there for fuel. And so if we're relying on that and we're, off by 58%, let's say, in terms of our classification, we could either be under predicting or over predicting risk pretty substantially around our communities. So it isn't to say it isn't useful. We use FBP all the time operationally to say, like, is the fire behavior I'm seeing on the ground reflect the fuel type that it's in? And if it isn't, do I need to recalibrate my thinking to estimate fire spread? But when we're using it to assess risk like this, it can become a little bit more challenging. So what other data types can we use to kind of like fill some of these gaps in our knowledge and the uncertainty that we have with this stuff? So this kind of brings me to sort of what we've been working on for the last little while. And actually the motivation for working on this, it started in 2021 when we were approached by Rogers Communications, who's been our partner on developing the system for the last few years. And it actually came from a fire that I worked on. It was back in 2006. And so this is actually from that day. It isn't actually the right day. I couldn't remember. It's a long time ago for me. I can't remember the exact day, but I have video from it. And it was a day like this where the fire weather index for the day was quite low. So the predicted fire behavior we were in Alberta in Hinton. The predicted fire behavior for the day was like, if you're going to get a fire, it's not going to do a whole lot. It had been raining for weeks. And so as a crew, we were on 2-hour getaway, which meant that if we got called, we had 2 hours to get to the helicopter and take off and go deal with whatever it was. Because overall, based on our weather stations, we weren't predicting much risk for fires that day. So we got called, and so we kind of go to the helicopter, meet the pilot, and you go fly off. And as a firefighter going to a fire, when you have this kind of conditions, you're already starting to develop this conceptual model of what might be out there that you're going to respond to. And this is what you would probably expect. It's a lightning strike, it's hit a tree, it's smoldered around for a few days, we got some sun, and it's going to kind of puff up. So we're going to show up there and put it out pretty quickly. So as we're flying towards this fire, we kind of get into the valley, and there's actually quite a large column waiting for us there. So we're a crew of 7. So we called for additional resources, but there weren't any. There's no more helicopters because the risk is super low. The air tankers weren't available or on like 4-hour getaway. And what we ended up actually responding to that day was this. So this is about as aggressive fire behavior as you can see. So rank 6, 200 to 300 foot flames burning through pretty dense lodgepole pine, spotted across that lake. We lost a few structures and some very remote cabins on this fire. But it just sort of reflected that, what we expected for the day was not what we responded to. So when we went back and looked at the fire weather stations for the day, the 2 closest weather stations were about 500 kilometers apart, and this fire occurred almost directly in between them. So we have these gaps in our knowledge of and our understanding and monitoring of what our fire risk actually is. So this fire was super remote, probably not a big deal, but around our communities, we actually have a lot of these same gaps in terms of our understanding of fire risk. And we've seen the impacts of this. It's kind of struck me a little bit in the last few years about how we have fires that impact communities. And after, there always seems to be a little bit of surprise in terms of that fire was way worse than we expected it to be. And a lot of that has to do with our ability to kind of monitor our conditions and what our fuels are actually doing around our communities. So the West Kelowna, the McDougall Creek fire, for example, we had that ignition, the conditions were pretty ripe, and then obviously a big cold front comes through. But there was always this sort of sentiment that's like, wow, that was way worse than we expected it to be. So how can we help kind of fill some of these knowledge gaps? And so what we've been working on since 2021 is this low-cost Internet of Things device. And so basically, it's pre-made hardware that we've developed firmware to run on, and it's a weather station. And so these stations are monitoring temperature, relative humidity, wind speed and direction, precipitation, soil moisture, and soil temperature, and we're adding in solar radiation and PM 2.5. They're monitored pretty much continuously. So we can program them to monitor everywhere from like a few seconds to record measurements up to a few hours, depending on what we want. And then the data are transmitted over cellular networks back to kind of the system that we have running in the background. We're actually working right now on integrating satellite into this because there's a lot of areas and communities that we're working with that don't have cellular where we're working. And so what we do is we've deployed a few hundred of these stations right now in the Okanagan in southeastern BC, and we're moving into kind of northern BC. We then start combining different data sets that allow us to kind of assess the fuels that are associated with our sensor network. So this is just two examples of two very different fuel types. The one on the left is quite dense. The one on the right is kind of a bit more of an open ponderosa pine bunchgrass ecosystem. And so what we use then to assess our fuel types is technologies like satellite data and light detection and ranging. And here, this just is an example of a point cloud that we collected. This was from an airplane, but we also use drones to do this kind of stuff, where we can actually assess what the fuel complex looks like structurally. So you can see an example of a tree there on the right, where you can kind of see how the canopy is structured, what the ladder fuels might look like, and then what the surface fuels might look like around it. So we develop estimates of the actual fuel structure that are a little bit, well, they're quite a bit higher resolution than what we get from the FBP, because we not only know that it's like, let's say, a ponderosa pine, but we know how much biomass there is in the canopy. We know how much biomass there is or how much structure there is in the ladder fuels and other kind of things like that. So basically what happens then with our system is we get this really high resolution very high temporal resolution weather data coming in from this grid of sensors that are distributed around communities. And what we sort of found in like the Okanagan is that having a station, every 10 to 20 kilometers, even a bit more if the fuels are fairly homogeneous, gives you a pretty good idea of what's going on. And for being so low cost, they provide really quite reliable data. So we can actually see here, this is kind of your temperature over time and your humidity. So we see the offset where the temperature is going up and the humidity is dropping. We're actually capturing when, precipitation events are happening across landscapes. With just one weather station, you oftentimes miss out on kind of like sparse precipitation, which is something we get a lot of in the Okanagan. And we're getting this really high resolution information on kind of wind speed and how that's changing over time associated with these given locations and kind of the microclimates that are associated with the site. And so what we do is we're essentially taking that data and we're translating it into, so here we have kind of the same weather data over time for a whole bunch of stations for a given region. And we're basically going through and starting to be able to predict what are your high risk periods associated with these kind of like these data streams. So based on, your humidity dropping really hot, really quickly, your temperature rising really fast, and then translating that into those FWI indices that I talked about earlier, where we see our fine fuel moisture code is going really getting really high. Our drought code is going up, and because of that, we're going to have higher ISI and BUI values. So we're combining all that data with satellite data and with LiDAR data to be able to kind of predict in real time what fire risk is going on, what's happening around our communities. At the same time, over the last few years, we've had crews out essentially collecting what are fuel moisture samples. And so we'll go out into the field. Students or our crews will collect different diameter of fuel types that I talked about, fine fuels like you can see here that look very nice. We'll go out and we'll collect live and dead fuels, and then we'll essentially weigh them. We'll dry them for 24 hours or longer if needed, and then we'll weigh it again. And what it essentially gives us is an idea of the fuel moisture content in that fuel type. And so on the top here are our small diameter fuels for a given season and the percent moisture in that fuel type for fine fuels in the Okanagan. And you can kind of see as we're getting into July and August, there's almost no moisture content left in that fuels, those dead fuels for this location. Here we've got a little bit larger fuels, something that's more like the Duff moisture code or that size diameter fuel. And you can see that they're also dropping quite rapidly, but they don't kind of dry out to quite the same degree. This is really important because what we're trying to do is understand with our models how our fuels are actually drying out to predict that type of risk associated with that fuel type is available to burn, rather than just saying like, well, we might see this type of fire behavior in a general fuel type. So we're trying to link that much more mechanistically with these models. And so what we basically do, we have two different sort of assessments that we do. And so we've been using AI to kind of process these really, really large data streams that are coming in to be able to generate data rapidly enough that it could be used operationally. So the FWI system, they generate one prediction per day, and it's going to be, this is your FWI for the next day at, they take the 12 p.m. prediction. It's going to be for 12 p.m. observation. It's going to be for 4 p.m. Well, how's risk going to change in between that? What's going on spatially and temporally around our communities? So we've developed this wildfire susceptibility index that we're now working with agencies on to look at for assessing. It basically uses these gated recurrent units and graph convolutional networks to aggregate all this data together. So weather, FWI, and vegetation metrics to predict for these large grids across time. So this is kind of every 3 hours, but we can do it sub-hourly, how that risk is changing for that region. And so you can kind of see, like, you can't see the map underneath it, but for this area, we're kind of seeing, fire risk increasing to about 6 p.m. and even later into the evening in this day in the Okanagan. The other one that we're working on, and this one is still in development. So the first one we're kind of testing with kind of fire departments and wildfire agencies. The second one is the fuel moisture risk index. And this is a physics informed neural network where essentially it relies on some of the models from the first one, but we're actually incorporating in those mechanistic properties of fuel moisture and how they change diurnally and over time to be able to predict at very, very high resolutions what we think the risk might be associated with fire for a given area. So this is an example of a 5 p.m. prediction from that model for an area just north of the campus in Kelowna. And at 5 p.m., it's really interesting. It's kind of a mountain. And those blue areas are kind of your eastern aspect, and your red areas are your west aspect. So that model actually predicts how your fuel moisture is changing relative to also the solar radiation that you're going to get at a given site and what the sensors are kind of telling you for that area. So that one we're quite excited about because that one really allows us to then step into being able to predict what type of fire behavior we might see at that site because of the fuel moisture content that's available to burn in those fuels. And so how are we integrating all this? I'll kind of wrap it up. And so the system's sort of been tested in the last few years. In 2023, so this is the McDougall Creek wildfire on the Thursday, just as it's kind of, this is a Planet Labs image at about 1 p.m. It's just as the fire is kind of standing up to take its run into West Kelowna and into Kelowna. And the fire behavior that we saw that night was incredibly dramatic overnight. So this is probably around 8 p.m. looking across the lake from Kelowna to West Kelowna. This fire spotted across a 2 kilometer wide lake like it wasn't there. We were getting pelted by debris and flying embers on the other side of the lake. So, it burned as an aggressive surface fire through a lot of these areas. And again, sort of exceeded the capacity of fire suppression organizations to respond, and obviously had a big impact on our community. But what we had at the time, we had sensors out through this entire area, but we were still in sort of this kind of like testing phase. And so those red dots that you can see are some of our sensors that were out in the area. And so when you're developing these types of models, we didn't want to be blasting over like X or Facebook or anything, what we were expecting for fire behavior and risk, because that wasn't integrated yet with like, the Kelowna Fire Department or the BC Wildfire Service. We were still in kind of that testing phase. And so 15 of our sensors got burned over, and that night and the next day. And this is actually a graph that you can see from one of our sensors where we had, 30-degree temperatures. It actually drops, the temperature drops, and that's actually the smoke plume over top of the sensor, keeping the temperature lower. And then you can see it spikes to 50 degrees, and that's actually when the fire hits the sensor. So even as like an early warning system to say like, with all this fire front, where is the fire actually hitting things? This kind of gives us a bit of an early warning system. So we're working on a paper now to sort of assess like, what was the residence time of the fire around some of our different sensors, and what did we see in terms of fire behavior that night and that day. And so as an outcome of that fire, and unfortunately, it's sometimes how it goes where an event causes, or it's like, hey, we should all work together on this. So we've been partnering a lot more with municipal fire departments. We're getting a lot more of these sensors out around communities, and like, working with the Kelowna Fire Department, for example, and getting these out. And we're starting to develop software and dashboards that allow them to kind of interact with the data. And so you can log into this and you can click on any one of your sensors, and it'll give you your raw weather measurements. It'll give you your FWI indices, and it'll also give you your predictions from our fire risk models. When they show up in the morning, every single one of the stations automatically emails, well, the station doesn't, we automatically email an assessment of, for that day, what is your risk? And then what is it going to be for the next 3 to 5 days based on the long-term forecast? So you can kind of come into the office, sit down, have a coffee, and you can kind of see what you might expect for that day, and filling in some of those gaps that we have with our existing stations. The final thing that's kind of happening with this system right now, and this is going to be a large expansion, is we've signed an MOU with the BC Wildfire Service to lead the provincial wildfire camera network. And so what this is going to be is pan-tilt zoom cameras that are deployed on cellular and satellite infrastructure across British Columbia that you've probably seen to detect fires using computer vision and AI. And what we're hoping to do with this system is integrate it in a way where you have a detection, and we're automatically pulling in our sensors to say, well, here's your wind speed. Here are your various parameters that might influence fire behavior, and then deliver those automatically to those responding crews, whether they're municipal fire department or the wildfire agency. So it kind of gives them an idea of kind of what they're going into that, when I worked in 2006, we really didn't have. And so there's a lot of excitement about this type of system. The last thing I kind of say, and then I'm going to wrap up, is that by putting these sensors into different areas and keeping them there over time, we start to see these patterns of risk that are vary a lot across landscapes. So areas around communities where there's just persistent chronic risk, the fuel type, the type of weather we see there, it just drives high risk for those areas. So the other thing we've been working on with BC Wildfire Service and some other partners is getting these sensors out onto prescribed fires. So you can put a whole bunch of the sensors out, and they're giving you different information about what is going on in terms of risk and the parameters you're interested in. And it's giving us information on, like, if we're going to do mitigation, Where should we target our mitigation? If we're going to do prescribed fire, are we in the right window to deliver fire safely to kind of achieve the ecological objectives that we're interested in? And Keith kind of mentioned, and it's very exciting, but we've been working with a foundation for a year, the Weston Family Foundation, and we're close, or we've closed on funding to develop a Canadian prescribed fire training program out of UBC Okanagan. And so this will be training folks from anywhere from, you're a crew member getting involved in prescribed fire all the way up to burn bosses. And so we're really excited about how, we might use these type of technologies and things to help better protect our communities and mitigate fire risk, kind of going forward. So that's all I have. I'd say, just my last point is like when we're developing these models, like I said, is one of the things we're really focused on is like how, like you're running an AI, but how do you make sure that the data you're delivering to crews or the community partners we're working with is the information that they need to see to make decisions and not get just bogged down with all the complexity of what the AI is doing. So thank you very much, and I'm happy to answer any questions.
Awesome. That was great presentation, Matthew. Very much appreciate it. Before I get to the questions, so I wanted to give a little bit of context since many of us don't have an intuitive feeling of what 15 million hectares means or 5 million hectares. 15 million hectares, if my math is correct, that's 1.5% of the land area of Canada.
Yes.
So 2023 burned down 1.5% of the land area, 1/60th of the land area of Canada, and 2024, 5 million hectares, that's 0.5%. So basically, in the last couple of years, average of 1% of the land area of Canada is involved in wildfires. Is that right?
Yeah, it's pretty close, I think. And you start stacking those up year after year because it's not necessarily the same things that are burning for fairly long periods. It's starting to really add up.
Yeah, I mean, and for a little bit more context, that's 0.5%. The 2024 figure is 60 times the land area of Calgary and 80 times the land area of Toronto. So 60, 70, 80 large cities burning down every year, out in the, not in the city, but that land area. But before I go to the questions tend to be about points you made during the talk, but I want to sort of get a big picture. I want to ask you a big picture question. Presumably, the system is too new for you to be able to say anything about improved outcomes. That it's too new to have made a difference in like reducing numbers of fires and whatnot. But can you tell us something about? I mean, maybe I'm wrong about that. You have some improved outcomes, but can you tell us something about how firefighters feel about their knowledge state or how they are how they've changed the allocation of firefighting resources?
Yeah. Yeah, it's really hard to assess like, with wildfire, this system caused this amount of reduction in, number of fires. It's even hard to assess sometimes like the efficacy of our crews. That crew got there at this point and they just managed to catch that fire versus they didn't and that fire got away. So I think with something like this, one of the sort of metrics that we've been looking at in terms of like value for partners, and some of the ways we're expanding this, we're working with First Nations communities and like organizations like the First Nations Emergency Services Society to get more of these out around First Nations communities, and working with fire departments like the Kelowna Fire Department and BC Wildfire Service about in areas around their community, you if you're the local agency or the local community, you generally know where your kind of pinch points are in your high risk areas. And so by putting these things out into those areas, we're helping sort of like fill that knowledge gap of we know that's a priority area for us, but we don't actually know what's going on there. And now you have actionable data to say like, all right, we're seeing risk kind of fluctuate throughout the season in this area. Based on the forecast, we expect, this area might be a problem for us, this weekend or something. And so one of the discussions is around, if you're a municipal fire department, if those priority spots might be a problem coming up, maybe you stand up an extra engine for the weekend, and maybe you pre-position your engine or something like that, or a crew in a specific area that lets you respond faster. Because initial attack, everything depends on getting there as fast as you can. Um, so that's been one thing. I think also though the utility in prescribed fire and mitigation, just that understanding, I showed the provincial strategic threat analysis. A lot of BC just looks like high to extreme risk, but it's a lot more nuanced than that. And so, if you're only getting a certain amount of money every year to do risk mitigation, by using data like this, we're now being able to say like, well, these are our kind of our if we're going to stratify things, these are the ones that we should target first. And if we're going to use prescribed fire for that, how do we, monitor conditions to make sure that we can put prescribed fire back into that landscape safely? The other thing that's been really helpful about it is in stands where we're doing mitigation, you put it in first, you do your mitigation, and then you leave the sensor in after. And so we can actually do pre and post monitoring to understand like how much are we reducing fire risk in these actual stands.
Cool. One last question before I ask our attendees questions. You talk about low cost weather stations. You turn that into dollars and so on. I mean, how low and how big, if you were to put out a reasonable, a number that might be reasonable in terms of being no more costly than cost beneficial, right?
Yeah.
Without going nuts. How many weather stations are we talking about, and how many dollars is the investment gap?
Yeah, so the stations that we're building, there's a few variants. We're testing some new ones that we're developing. They generally run anywhere from like $800 to $1,200 per station, based on the power draw and kind of the optimization we've done for data delivery. They should stay operational for 3 to 5 years based just using batteries. Solar isn't the most reliable option when they're in the forest. If they're in an open area, you can use solar. Um, in terms of like how many around a community, I mean, uh, in the Okanagan, as just an example with McDougall Creek, there's two weather stations around Kelowna. There's one that's maintained by the fire department in West Kelowna. There's one kind of down by the airport. Um, those were the two stations that they were drawing information from when they were responding to the McDougall Creek fire. Those stations, they'll generally run 20,000 plus for that kind of weather station.
Mhm.
So, it isn't that you need hundreds around a community or anything like that. We've been kind of prioritizing where we're putting it. But, even some of the communities we're working with, it's like having 6 to 10 around the community is that much more data on what's going on in terms of your weather parameters and your fire risk versus one weather station that might be 60 kilometers away. And so when you're responding to a fire, when you're thinking about risk, there's so much more going on. And we've also compared it to satellite estimates of kind of, what we're getting for temperature. We're pulling in Meteorological Society of Canada long-term forecast data into the models. And so that's sort of like where we're going with it. So, I mean, you can get 20 stations out for the cost of one kind of thing.
Right. So we're just doing the math. That's about $3,000 per year, $3,000 per year to have these stations around one community.
Yeah.
Awesome. Okay, let me turn it to questions that our attendees asked. We had early on, we had an anonymous question. I'm not quite clear on the meaning, but I'm going to try to reinterpret it. An attendee asked, basically, do the historical data support the notion that wildfire is a renewal process? That is, you build up fuel, it burns down. So the next year, so you go from a high risk year to a low risk year. Is that what the data actually show, or is the country so big that low activity in one place is offset by high activity elsewhere?
Yeah, it really depends on kind of the ecosystem. So, in some like those fuel limited systems that I mentioned, you would have so much you would have historically had so much fire activity that you wouldn't have had a lot of fuel accumulation happening in those systems. It would have maintained kind of an open ecosystem with some accumulation of ground fuels, maybe a little bit of regeneration, but fire would have been coming through so often that you wouldn't have seen that kind of accumulation. If you look like nationally, um, we've just had so much departure from those historic fire regimes that you could almost say, like, I'm overgeneralizing, but there's probably substantial fire deficits in a lot of our ecosystems naturally, where they've missed 1 to 10 fires compared to what they would have historically had. So how much fuel accumulation you're going to have through that is going to be substantial. Now, that isn't to say like, when we say 15 million hectares, uh, not all of that's high severity. It's incredibly diverse, and we talk about pyrodiversity. You're going to get a lot of low severity and moderate severity fire and high severity fire where it should happen also. That does reset the ecosystem. It does reduce the fuel loads. It can act as a restorative process. I think what we're seeing though is we're getting more high severity fire, and that's the type of fire that it's taking out almost all the biomass. Sometimes it's burning
Mm,
right through kind of the soils. What those landscapes will look like in the future is a big question. Are they going to return as the same type of forest? Are they going to transition to some kind of new like shrubland ecosystem? That's a big question. And the other thing that we're kind of seeing, and some studies have been done by the Canadian Forest Service in the boreal, is that past fires sometimes aren't providing as much protection as they would have historically, and they're reburning sooner than we would think. So, if it's a high severity fire, something isn't going to go through something that doesn't have any available fuel. But if it burned at moderate severity, you can get a fire come through that like right away, like the
mm,
next year.
gotcha.
So we're seeing more of that, which kind of indicates that like you might not be getting sort of the same sort of protection you've had from historic fires.
Gotcha. Understood. Stu Clark from Whitehorse asks, how does the density of built fuels compare in risk to dense forest? Meaning, how did, if you were to compare, I think he means if you were to compare an urban area in terms of fuel density to a dense forest, how do they compare?
Um, so I think if we're talking about like so one interesting thing, like maybe just context, what I'm going to say is that like for a lot of our urban fuel types, let's say, like the tree you're gonna plant next to your house, or the cedar hedge that everyone has in the Okanagan, or the mulch, or like those kind of things. We actually don't understand a lot about how those fuels burn. We've focused a lot on like, how ponderosa pine burns or Doug fir or something like that, like our natural sort of fuel complexes. And so I would say like the challenge with the urban environment is like the fuel density that you get in a forest, like a regenerating lodgepole pine, you can have like 50,000 stems per hectare. It can be incredibly dense, regenerating fuel types right up against communities. So I think in terms of like overall biomass of natural fuels, our wildlands are where it is in terms of fuel type. The challenge that we get when it gets into the urban environment, like we saw this in Los Angeles a little bit, where you just have incredibly high housing density and you have it intermixed with all these really volatile fuels. We saw that in the Okanagan too. I mean, cedar hedges were probably one of the bigger contributing factors to losing homes. You get these really complex fuel structures, but then you also have this interaction of just that built environment burning with natural fuels. And as a wildland firefighter, you can't even operate in that space anymore because you're not equipped to fight fire there. Um, so in terms of overall biomass, I think it's definitely in our wildlands. but it's just more complicated when we get into those urban environments. And one of the things we're working on funding right now at UBC Okanagan is a new state-of-the-art wildfire lab, where we'd be able to do some of that fire simulation and experimentation where we can like build structures and we can put hedges and mulch and all kinds of stuff in there and light it on fire to see how different kind of things react.
Kira Conrad asks, is there a national wildfire mapping resource that you would recommend for our audience to refer to when they're looking at wildfire risk? And by our audience, I mean largely insurance executives. And
Yeah,
how is that resource updated?
yeah. There's that's challenging because so the fire danger stuff that I showed with the wildfire with the fire weather index, you can go to Natural Resources Canada and they update that every single day. So it's the Canadian Wildfire Information System that gives you your basic maps that are based on all the weather station data across Canada. The national mapping, though, is challenging because risk and fuel assessments and all that kind of stuff is such a provincial and territorial obligation that like how BC approaches it is going to be a little bit different than how Alberta might approach it in terms of like how they're going to map things to assess risk. So like the provincial strategic threat analysis in BC is very different from what you might see in other regions.
Mhm.
So for national mapping, I'd say the best resources are things that come out of the Canadian Forest Service for a lot of that. But it doesn't get granular enough oftentimes to give you information about like what's going on around a community. It might just tell you for like landscapes what the actual risk is.
Gotcha. Thanks. Um, let's see. Lyle Unwin asks, if post-wildfire conditions are worse than expected, should we perhaps reconsider the metrics we're using? Precipitation, for example. An early slide showed an increase, yet other metrics decreasing or becoming worse. Is precipitation, I guess he's restating, now or becoming misleading and perhaps masking a governing metric?
Yeah, there's a lot going on, I think, in this monitoring. Like even you update it another year and it's like, oh, that's a little bit of a different pattern just because we saw such like maybe we were in an El Nino one year and then we're in a La Nina and then we're out of it like we are this year. We're in this weird gray space between them. Um, I think like what we're really relying on with fire weather specifically is long-term trends. So, you know, we're seeing more precipitation, let's say in BC, but a lot of that is driven in our coastal ecosystems. So we're seeing more, but then we're also getting higher temperatures. And so you're just seeing more evapotranspiration that's happening as a result of that precipitation. Um, I think like
Sorry,
one of the challenges sorry.
evapotranspiration, that's where evapotranspiration, for the people who aren't familiar with that term, it means moisture coming out of the plants and going into the air. Is that what that means?
Yeah, exactly. So we're, you know, we might not be retaining a lot of that moisture. Um, I think the challenge, like what we're dealing with right now, is like, you know, the FWI as an example, it's used operation, it's been used for years. People really understand it. And so when you're trying to bring in new systems or new models to assess this, it's always going to get compared in terms of utility to what we're already using. What is it going to fill in terms of information gaps? How user friendly is it? Um, and I don't think like the challenging thing with wildfire is like there's no one lever that it's like, oh, it's definitely just that. It's always this really rich mixture of like, well, the temperatures and the wind speeds are doing this, the fuel type is this, but you're in this type of topography, and so you're going to get this type of risk and fire behavior. So I think like that's where we run into like working locally with communities and agencies and the folks who know their landscape and the ecosystems is really important because
Mhm.
that's where you develop those sort of local solutions to, you know, risk and kind of fire management.
Yeah, cool. Sarah Law says, do you run into any resistance for prescribed fires? And do you have any data to show why they are or are not effective?
Yeah, so yeah, there's definitely resistance. I think that's changing. I think it depends where you are in the country. Like I think in a lot of regions of British Columbia, for example, like where we do a lot of prescribed fire in the southeast of the province, there's a lot more acceptance of it because we've been working in that region for years on building that social license and under public and policy under or sorry, public and politician understanding of what prescribed fire is and why it's important. And so I'd say there's resistance in the sense of like people don't like to see burnt landscapes. And so a big part of what we work on is that public messaging of like not only why this is important from maybe a risk mitigation standpoint, but that fire is a natural part of this ecosystem. And by putting it back in, we're actually restoring this ecosystem that you really enjoy recreating in or that's important for resources. I'd say one of the things, the bigger challenges right now, and so with this program that we're developing, we're going to need to work on building that social license across the country. We're going to have to get into these areas where maybe there hasn't been a lot of prescribed fire and help sort of do these demonstration fires and help people understand why this is important. I'd say one of the things though that we're running into that is really challenging and is something that it's very top of mind when we're putting fire back is smoke.
Mm.
Wildland fire smoke is just bad for your health. And so working with local health agencies to help better prepare people for the idea like, hey, there's going to be a prescribed fire. If you have any of these kind of risks, we recommend, you take these precautions. And then we're trying to burn under conditions that allow us to disperse that smoke so it's not going to remain there. I think there's a little bit of confusion around or fear around it though, because it does have impacts, but an 800,000 hectare fire like Donnie Creek is going to put out more smoke than we'll probably ever put out in prescribed fire in BC in a decade. So it's kind of comes back to like how do you want your smoke but making sure we have the messaging to people to help them understand and prepare for it.
Thanks. Johanna Brady asks, and I think you've given us an anecdotal answer to this. She asks, what's the granularity of your sensors versus the existing weather stations? Relatedly, is there existing information about the density of existing weather stations and how it varies geographically, such that a measure of confidence in FWI could be generated? That's
The weather station networks, so there's a variety of them. I'm actually very curious to come to your talk next week to hear about aggregation of weather station data. That's great.
mm-hmm.
Environment and Climate Change Canada maintains a network through the Meteorological Society. You might have airports that have weather stations. The map that I showed is BC wildfire weather stations. So they're operated independently from the federal networks. And so BC has 260-ish stations across the entire province. You'll see in some area, like you can go get the locations for every single one of the stations. All the data are publicly available. The density of the stations will vary across the country. Alberta has a lot. Yukon, it's mostly around like kind of populated areas. So it really varies a lot.
Mm.
Well, we've been focusing on, I'd say on average in BC, if I'm just using it as example, we have way more stations in our populated areas than we have in our north. And so the north, there's a lot of uncertainty. We don't have a lot of data up there. I'd say on average, they're, 60 to a few hundred kilometers apart, and you can have mountain ranges in between them. You can have all kinds of variability. And so what we've done with our sensors is, when we're focusing on a landscape or we're focusing on a community, we'll put them out we've found 10 to 20 kilometers gives you enough distance that you're not just replicating the last value kind of thing. And then we can actually, over time, start predicting for areas where we don't have stations. So if you have a dense enough grid, you can start interpolating or predicting for the intervening areas. In terms of uncertainty, the thing with FWI is that there's always going to be uncertainty. It's a very general model. Like FMC of like 91 versus 93, there's not that much difference in it. Like it's not that sensitive. And so it's again, it's sort of like, are you picking up those trends and patterns that are persistent across time, that we're really interested in? So I'm not sure that exactly answered it, but hopefully a bit.
Thanks. Yujin Yin says, this is awesome. Thank you, Dr. Mathieu. Do you know or are you aware if similar systems exist in the United States?
There's similar things to that camera network that I mentioned. We're essentially, using the model that they've developed in California. It's called Alert California. It's in partnership with UC San Diego. So that's kind of the model that UBC is using. I'd say in terms of sensor networks, yeah, there are similar things. We have, stations like this, weather stations. There's a lot of different types. They generally can be quite expensive. I'd say where a lot of the innovation's been lately, or a lot of the focus, isn't so much on modeling risk. It's on detecting fires as fast as you can. So using like volatile organic compounds or other kinds of like gases that are present in the atmosphere with low cost sensors to be able to detect where a fire happened. That's where I think a lot of focus has been, is more on detection and less on like risk modeling and understanding, before a fire happens, what might be the potential for that fire.
Okay, thanks. Jadzia Rudolph asks, is there a link or anything you can share for a resource, or how do we check out these new technologies? Is your network available to the attendees here today?
Right now it isn't. I think it's because like with the partners that we're working with, there are sensitivities around like the data, like they're using these for operations, and we're still kind of testing stuff. And this is what I meant earlier. Like we haven't made it public because we don't want something that's conflicting with the provincial messaging around wildfire risk that might be associated with FWI. So until something like this is a bit more integrated in with those operations for emergency management and public safety and public messaging, we probably won't make our dashboard public. But if people are interested, feel free to reach out to me. I'm happy to kind of like set up a time to kind of talk and show what it can do. Um, but with that being said, like our partners and the agencies, they have like full access to it. And that's the goal and what we're working towards is like, how do we integrate this in with how the province is managing wildfire risk? And then rather than having two separate systems, ours is just part of the greater whole of those 260 stations plus whatever else is going on.
Cool. I think you've answered one of the last questions about how other stakeholders like Canadian fire chiefs would get access to the data. It seems like they'd call you directly.
Yeah.
And Kevin Deneen and Jadzia Rudolph, this is for everybody else, have just shared links to a couple of resources. We've got just a couple of minutes left, and I wonder if you have any final words before I close things out.
Just thanks for having me. It's nice to be able to come and talk about this stuff. I'd say there's it can seem a lot of like doom and gloom when we talk about wildfire. But I'd say like in the last few years, we're making like a lot of progress on like a lot of things that are going quite well. Systems like this, partners that are doing great work, work on the wildland urban interface, the work your group's doing. Um, there's a lot of progress. And so I think it's just about maintaining that momentum. If anyone has any questions, yeah, please feel free to reach out.
Wonderful. Thank you so much. Matthew's talk, as I said, is going to be available at our website at www.iclr.org/workshops. The video, his deck, a transcript, and so on. Remember that next month, not next week, on June 13th, Connell Miller from the Canadian Severe Storms Lab is going to tell us about the Northern Mesonet project. That's that aggregator of weather data from around the country that's up and running now. He's got a lot of networks already available. So just Google, if you're interested, Google Northern Mesonet project or the Canadian Severe Storms Laboratory, and you'll find it as a project, Northern Mesonet project, as a project under the Canadian Severe Storms Laboratory. With that, I'm going to thank you once again, Matthew, for this great presentation, for the research that you're doing, and I'm going to thank all of our attendees today for coming. Tune in again next month. I'm looking forward to seeing you, and have a great weekend, everybody.
Thank you.
Bye-bye.